And two announcements just at the start here. First is that Lab 8 is posted on Canvas. Again, there's a PDF document. There is a Word document. They're identical. There's two videos to watch. The lab has two parts today. One is measuring a spring constant, measuring the Hooke's law spring constant for a particular spring. Two scenarios. We'll put one spring and then two springs together. And then the second is putting a spring in between two carts and having the spring push the carts apart and figuring out what the speed is and what the momentum is after the spring does that. So two videos to watch. They're pretty short, like 4 or 5 minutes for each, just showing you what we're doing in the experiment. And then you should find a handful of log group profiles, I guess two of them, from which you can get your data. And then there's also some data that you have to analyze that's in the lab handout itself. And so that's what's going on. Professor Kem should be sending out his link. He usually, I guess last week it was about 10 minutes before class, he sent out the link for my sections tomorrow, just the normal class link, just like always. Now there is no lab scheduled for next week. And nobody objected. I just had a couple questions on the timing for the exam next week. There is no class scheduled for Wednesday because it's the advising day. What I'm going to do is I'm going to put out, publish on Canvas and in Mastering the second midterm. I'll make it go live at 8:30 in the morning, the normal start class time. And then I'm going to give you 36 hours to work on it. So that takes you through till 8:30 on Thursday night. And if that's a hard spot with anybody, let me know. But I think that was an agreeable time for everybody, and nobody objected to moving it from Friday next class until next Wednesday and Thursday. So that is going to be the plan here. And I'll send you out a revision. Let me make a note to myself: a revision for the schedule, that little Excel document that shifts things around. But the bottom line is Monday's class is now going to be on Friday in place of the exam, and then Wednesday's class will back up to Monday, and of course the exam will be on Wednesday, and we won't lose any time. All right, any questions on that? All right, then let's get on to the material at hand here today. While I was talking, we got 27 people now, so we're only missing a handful, just two, I guess. We're talking about rotational momentum, angular momentum. And of course, there'll be a rotational impulse, and that rotational impulse, remember, a force provides an impulse. That's a force over a time, times a time. Force times time is an impulse, and that changes a linear momentum, what we call P, the mass times the velocity. Well, a rotational impulse, hopefully you expect. Let me show you a slide here real quick, rather than just talking to it. Share this with you. And I see the green border. Let's make that go away. And let's make that smaller. Okay. Since torque is moment of inertia times angular acceleration, I've solved for the angular acceleration here. And angular acceleration is also the change in angular velocity over the time. I can set those two equal to each other, cross multiply, and you see that the torque times a time interval. That's what I'm calling a angular impulse. I don't have a symbol for it like J, like I did for impulse along a line, but it exists. That has to be equal to moment of inertia times an angular velocity change, okay, which is a change in angular momentum, because then we go on to define angular momentum as a moment of inertia times an angular velocity. And this, I put that on the slide just to remind you of what impulse along a straight line was. Okay, the rotational analog is precisely the same thing, just substitute torque for force. Time interval is time interval, no change there. For mass, you substitute moment of inertia, and for a change in velocity, you write in a change in angular velocity. And so, there's a set of analogs between rotational motion and linear motion. Okay, and there is also a conservation law for angular momentum, just like there was a conservation law for linear momentum in the problems you did on Monday, where if you can look at what the momentum is at the start of the problem and you see no external forces acting on it, so no impulses, well, that momentum can't change. The change in momentum has to be zero. And then after some interaction, a collision, a separation of two masses with a spring, the momentum has to be the same, and that allows you to solve for some unknown quantities or predict some unknown quantities, and that's an important aspect of physics. It's a concept that we've got. Now, I want to show you real quick a video on YouTube I found. There's literally hundreds of these, and so I'm going to stop sharing that with you and start sharing the ice skater. Okay, I have no idea who this person is, but it says it's a world record figure skating spin because of the speed apparently that she reaches as she's doing her speed. And so let's just watch what happens. And I'm always struck by the relationship between sports, athleticism, and physics, because she only can do this because somebody's told her that if she does certain things, she can make herself spin faster. And so watch what she does. Okay, just kind of moving around, and then she puts herself in a spin, and notice her leg is out and her arms are out. And then as she brings them in, look how fast she's able to go. It says 308 revolutions per minute is what she hit on that spin. And so what's the physics behind it? Well, I guess that's Dorothy Hamill. No, that's Dorothy Hamill's the next one. We'll stop sharing that then. But I always find that impressive. Oh, look, Dorothy Hamill's going to do the same thing. Legs out, legs in, arms in, and you can see noticeably faster on the spin as she brings her legs and her arms in. Literally, you can watch, there's hundreds of these on the web. I'll stop right there. All right, close that so it doesn't keep opening up newer and newer slides. But I find that impressive and good physics, right? Because what we said is if there are no external forces, then the angular momentum has to be the same in the first case where she's spinning slow as opposed to the second case where she's spinning fast. So what did she change? She changed the moment of inertia. Remember, moment of inertia is a mass times a distance squared. And so keeping your arms out puts mass of your hands, mass of your arms at a great distance from your axis of rotation. And legs, same thing. It causes a large moment of inertia. When you pull them in tighter to your body, you create a lower moment of inertia. And if angular momentum is conserved, you have to spin faster to compensate for it. It is hopefully that simple, or at least hopefully that sensible. Looking for my PowerPoint here. Share that because we've got some questions to ask. Any questions on that idea of conservation of angular momentum? I think it's stated right here on this slide. Okay, you can see that the initial moment of inertia times the initial angular velocity plus moment of inertia of any other objects that are in the same system times their angular velocity is equal to some final moment of inertia times a final angular velocity, and as many things as you have summed. In the case of the ice skater, and I always hate that our textbook likes to put final first, but there's only one object, just the ice skater. So all we're doing is we're equating these two things, and her initial moment of inertia is pretty big and her angular velocity is pretty low, but that thing has to be a constant. And so what she does is she pulls her arms and legs in and she makes the moment of inertia go down. And so physics requires angular velocity has to go up and she spins faster. And that's the explanation for what just happened. Questions on that? Straightforward concept. It's now time to do problems because that's what we do in physics, right? And let me find, yep, there it is. I hit the right one. I have a question for you if you've got no questions for me. All right, then we'll open this up and I'll find the right one, which is always down at the bottom. All right, where is it? That's not a good sign. I don't see it. All right, well, I'm just going to ask you here. Let me create a dummy real quick with just A, B, C, D, E, and has it lost my poll? And I'll give you a second to think about that while I'm creating a dummy poll, and won't have the words, but it'll have A, B, C, D, and E, and you can just log right in for that. All right. Well, you're going to make me sign in this morning? Great. Come on, there we go. 2 seconds here. My apologies that it didn't save my questions, apparently. All right. A, B, C, D, and E. And we'll save that. Come on, I hit the save button. Do it. All right, put that away and try again. All right. Oh, I spelled question wrong, but we'll launch it. Pick your number. A, B, C, D, or E. It's kind of a review question, I guess. All right. Most of you got it on the right track here. I'm going to hit the end button as we approach a minute. And I'll share the results with you. D is the answer. Yeah, resistance to changes in rotational motion. Torque is equal to moment of inertia times angular acceleration. Just like forces cause accelerations, linear accelerations, torques cause angular accelerations. But the bigger the moment of inertia is for a given torque, the smaller the angular acceleration will be. Just the way it is. So it's the resistance to a change in rotational motion, because that would be an angular acceleration. Depends on the location of the axis of rotation. Absolutely. It's always nice when the axis of rotation is right at the very center, which it often is, but it could be at some other location, and that would change the moment of inertia. And if the mass is far from the axis of rotation, that makes the moment of inertia bigger, just like the example of our ice skaters. So all of the above's absolutely the right answer. And if you can keep that in mind, it makes your ability to think about the problems a whole lot easier. All right, I'm going to use the same poll here again for the next question. And we'll, I share the answer? Yeah, there we go. Mostly D, 17 people got it. We'll undo that and we'll run it again. Relaunch poll 21. Yeah, continue. You only have 4 choices here, but I'm kind of looking. Yeah, don't go E. Somebody's being smart with me here. You're funny. I know. If we were in class, I'd have a bunch of signs for you to hold up. A, B, C. Kind of asking you, what's the definition of clockwise and counterclockwise with respect to positive and negative too, aren't I? All right, I got 20 people in. I'm going about a minute and a half now, so we're going to cut it off in just a moment. All right, I'm going to end it and we'll share the results with you. The majority picked D, which I think is the right answer. Um, there's two parts to this, I guess. One is the torque piece, and then the second is the impulse piece, the rotational impulse, and then the change in angular momentum. And I always get asked the question, will there be review questions on the final exam? And so this material right here is going to be one of the focus areas of the final exam, right? Rotational moment of inertia and conservation of rotational moment of inertia is on the final exam. But if you look, this is a question here from chapter 7, I believe, right? So it's the province of the midterm exam next week. Physics is self-reviewing. It's self-reviewing. I don't have to create a review problem. I just ask a new problem, and it causes you to go back and remember what, for example, torque is in this case. What is moment of inertia? And I do want to point out that the angle right there is a 90-degree angle. I've seen people, as I'm grading things, taking some other angle that's given in the problem. Okay. I should tell you, it'll often be 90 degrees, because then the sine of 90 degrees is just one. Everything in the lab last week was a torque being a tension times a distance times the sine of 90 degrees, which is just one. Okay. So we have a torque here, I guess. Not given, but let's call the radius of this string here, I guess. The radius of the string, let's call it R, some number. So it's just R times that force. That's what the torque is. Okay. It acts on this object. I see somebody striking it this way, right? Putting that force on for some interval of time. And we said that a torque times a time interval is equal to a change in angular momentum. They're in the same direction, and the symbol's L. Don't ask me why, I didn't do it. Okay, so this force right here is tending to cause a torque that way, a twisting that way, an angular acceleration that way, okay, an angular velocity increase that way. And that would be, I guess, as I'm viewing it from the top, that would be counterclockwise. And we've said the mathematicians say counterclockwise from the x-axis, which is shown to be right there. That's a positive angle. Okay, if you move this way around that axis, the mathematicians have decided that's a positive angle. And so this is a positive torque. It's a positive angular acceleration. It's a positive increase in angular momentum, angular velocity. It's all of those things. So since it is going counterclockwise, the answer is positive, not B. Okay, it is going counterclockwise, but that's not a negative change in angular momentum. It's not a negative torque. It's not a negative angular acceleration. It's not a negative angular velocity. They all hang together. Questions on that? A couple of people got it incorrect there. Most got it right. So we'll stop sharing, and I'll go on to my last one here, and then I'm going to work a problem for you. So relaunch poll, continue, and this is our ice skater picture. Yeah, pretty straightforward when I show it to you in real life, isn't it? Yeah, excellent. Everybody's got it. Okay, so everybody's got the answer here. The one thing I want to remind you about the answer is physics as a discipline is focused less on that answer and more on the argument, the rationale, maybe even the mathematical proof of why that is the answer. So yes, we know the ice skater spins up. Why does the ice skater spin up? Is a speed up in the spinning? I think ice skaters call that spinning up. The reason is because the angular momentum of the person, they do things to cause it to be less, and that causes their angular velocity and therefore their angular momentum to increase. And so it's the reason that it happens is every bit as important as the knowledge that it happens. And I understand that's not a universal thing in all disciplines. In some disciplines, the answer is the most important thing. Always keep in mind in physics, it's the reason that that happens that is what we're often involved in a physics class and in a physics subject. Last chance for questions. All right, then I'm going to go on to the worksheet. We'll stop sharing this and I'll start sharing my iPad so I can work this problem here. Where'd the window go to share? There it is. Two screens. I love that it does this to me. It takes me back and forth between screens. Moves things around on it. Okay, a plugin's required today for something I've been using all semester. I'll install that plugin. It's that kind of day. Screen mirroring. All right, got that. And hopefully you are seeing my my iPad with the worksheet for today. And I'm going to do the first problem. And then the second problem, look at that. Who'd have thought? An ice skater. Okay, just with math. A little bit harder than the problem I did on the pre-lecture video. That's the one to work on after I'm done doing mine. Okay, so let's do mine. Mine is an angular impulse and change in angular momentum problem. Okay, and so let's see. Let's read what we got here and then label things. The angular momentum of the flywheel of this thing right here. This is a flywheel. All it is a device. Big trucks often have them. Just a disc, which once you start spinning, well, it wants to stay spinning. Your bicycle wheels are in some ways flywheels, right? That's how you're able to balance because once they get spinning, they like to stay spinning. And so that helps you balance because they like staying spinning in a particular plane. And so what we're given here for this flywheel, this thing that's rotating around right here, is I guess the moment of inertia of the thing. And then what else are we told? The angular velocity and applied constant torque decreases the angular momentum from 65 to 21 kilogram meter squared per second. That must be the right units for angular momentum. Talked about that on the video last night. So this must be the initial, that's supposed to be an I right there. The initial value, 65 kilogram meters squared per second. And this must be the final value. Okay. And so that's what we know. Oh, and what else do we have here? Handily given the time interval. If you want to write those out separately, I highly encourage that. That way you've got them clear in your mind. This is a technique that I've seen students use. Okay. I got all the terms identified in the problem statement because sometimes that's half the battle in all disciplines, other subjects as well, reading the word problem and making sure you understand what the given information is that you're going to work with. Okay, first question is what's the change in angular momentum? All right, well, the key equation, and I wrote them up at the top here for you. The key equation is that the angular impulse, the net torque, okay, times the change in time, the time interval, is equal to the change in angular momentum. This is pretty straightforward, though, I guess. I'm just looking for the right side of that equation. And now we just go back to what the definition of a change is. Like anything else, since week one of the course, a change in something is its final value minus its initial value. Okay. Anytime you see that upside, that triangle for change, delta, the Greek delta, that's what it means. And so in this case, it's just, let's see, final value 21 minus initial value. Looks like I'm not going to put units on, huh? Now I just factored them out because I'm too lazy to write it twice. But I will tell you, as I grade stuff, I don't see people putting the units here. And that is the thrill seeker physicist. If you don't put units on, you start multiplying and dividing things and you get an answer that doesn't have the right units, but you don't know because you haven't done the unit analysis, it's going to be wrong. And you won't know it because you didn't do the check. You didn't build yourself a safety net. That's why I refer to you as a physics thrill seeker. Okay, so in any event, I've got the change, whatever 21 minus 65 is, it's negative, isn't it? I didn't do it, it just turned out that way, minus 44 kilogram meters squared per second. That's the change in angular momentum. All right, so the next question is what's the torque? Well, that's good. I've got the equation, so torque would then be equal to that change in angular momentum divided by the time interval. By the way, I know a couple of you have had calculus. That could be a derivative if I wanted it to be, if I just made the time interval really small, but that's for another day. Back here, just a change. So what is it? I know what the time interval is because I circled it, although I just slid my, there it is, 1.9 seconds. We'll get back to it. Minus, pen please, minus 44 kilogram meters squared per second, divided by a time interval, 1.9 seconds. And let's see, what do I have for that? I have 44 divided by 1.9, put that in my calculator. Don't drop the negative sign, minus 23.2. Now, it's a torque. What are the units supposed to be? The answer is it's supposed to be a Newton meter. Many of you have probably memorized that has to be the units of torque. The question, though, and this is the thrill seeker aspect, especially when you move on from things that you're very familiar with, okay, when you're a little out of your comfort zone in a calculation, units are the thing that's going to keep you on the straight and narrow. So the question, I guess, is since I know that a torque has to have units of Newton meter, is that thing right there going to give me Newton meters? Okay, so let's see. I think that would be a kilogram meter. Watch this. I'm going to separate it out. And then I've got 2 seconds here. So that's seconds squared. And the reason I did that is because the thing in the brackets right there, that's a kilogram times a meter per second squared. I guess the first thing you have to realize is that those seconds don't cancel, right? It's divided by second divided by second. That's divided by second squared. Okay, so they don't cancel. And then the second thing you got to be able to think about is we'll split up the meters squared. So I got a mass times a meter per second squared. That's an acceleration. Sure enough, it's a Newton times a meter. That's what I needed it to be. There's a chance that number's right because my units came out right. Just how it works. All right, so now I got the torque. Let's see, little review question, I guess. What's the angular acceleration? And then through what angle did this flywheel rotate as it was slowing down, changing its angular momentum from 65 to 21 kilogram meters squared per second? Okay, so we can finish that up, I guess. And it's sort of a review problem for the midterm next week, because in chapter 7, 2 chapters ago, I guess, not last chapter, 2 chapters ago, we found that angular acceleration is torque divided by moment of inertia. In this particular problem, moment of inertia is given 2.7 kilogram meters squared. Okay, so I just have to put that in. I may stay with my original units here, the things I have circled right here. Torque, perfectly legitimate to go back a step, minus 23.2. Rather than writing Newton meters, write kilogram meters squared per second squared. Okay, because I'm going to divide that by, and I've forgotten the number while I was yakking here, 2.7 kilogram meters squared, right? 2.7 kilogram meter squared. And now you can see why I went back from Newton meters to the units before I simplified them, because that and that cancel, and I'm left with 1/second squared. Is that a unit of angular acceleration? Well, I've said in the past that a meter over a meter, right? Arc length formula, angle is just a distance s over r. It's a length over a length. It's a dimensionless unit. It's a placeholder unit. I don't have anything in the numerator right now. So let's put radians there because we can. Radians per second squared absolutely is a unit of angular acceleration. Put this in my calculator to get the numeric value, minus 8.577. Now I'm a little concerned about going 4 digits right there. In this problem, nothing is more than 2, so I should round to be technically correct, minus 23 Newton meters right there. And this should be rounded ultimately to 8.6 radians per second squared. But I'm going to use it in the next step. So let's keep all the digits that I've worked hard in my calculator to get. Okay, because then the next question is how far as this rotational inertia, as this rotational angular momentum is decreasing, does the flywheel rotate? And so you got to come back to an equation. Look at that, my stylus turned itself off. Theta is equal to the initial value of theta plus the initial value of angular velocity times the time interval plus 1/2 the angular acceleration times the time interval squared. Well, I just figured out what this is. I know what the time intervals are. Any objection to starting at initial angular angle of 0? And of course, what we want to figure out is what's the final angle after 1.9 seconds. There is an issue though here. Anybody remember being given that number right there? What is the initial angular velocity? Hate when that happens. It's not there. But look at what you do know. You do know the initial angular momentum, and you know the moment of inertia. So you can solve for what the initial angular velocity is, because it's a kind of a step you have to do before you can get to the step you want. The initial angular velocity is equal to the angular momentum times, the initial angular momentum is equal to the moment of inertia times the initial angular velocity. And so that tells me the initial angular velocity is the given angular momentum divided by the moment of inertia, two numbers that we know. 65 was the initial angular momentum. So this guy is equal to 65 kilogram meter squared per second divided by 2.7 kilogram meter squared. Same thing happens here again, doesn't it? I don't have anything in the numerator, so make it a radian, and it becomes a radian per second. Is that a good unit for an angular velocity? Absolutely. And that's just a matter of taking 65 divided by 2.7 in your calculator. I got 24.1 when I did that. Okay, we're on a roll here then. Now we can finish up the problem in the little space that I've left myself, because I've been writing like a gorilla with really big letters. But let's go back to that. I'll bring this down here, and we'll say that the final angle, how far it rotates as it's slowing down, is equal to now 24.1 radians per second times our time interval, which is still 1.9 seconds. That's the slowdown time. Okay. And then plus 1/2. Now be careful here. Look at what our angular acceleration was. It's slowing down. So it's negative 8.577 radians per second squared minus 8.577, sorry. 8.577, yeah, that's the right number, radians per second squared, and that's times the time interval squared. So that's 1.9 seconds squared. Okay, to keep myself from making mistakes, second squared cancels second squared there. I'm left with a number in radians. Second cancels second right there. Notice this term is negative. This term is positive, but it's bigger. So I put those all in my calculator, and I got 30.3 radians for my total angle that the flywheel coasts while it's slowing down. Okay, now just does that make sense? Is it a sensible number? 30 radians. There's about 6.28 radians every time it makes one turn. So this is somewhere between, looks like 4 and 5 turns, full revolutions it makes. And that's a good number. So that could make sense. My units worked out. I got some confidence that number actually is correct. All right. I do want to make a point on that, though. I was grading some of the stretching of the bar problems, and people were getting numbers like, 10 to the 10th meters. And I want you to kind of think about what 10 to the 10th meters is in lieu of the astronomical calculations we did, like what's the radius of the Earth? That's a huge number. And if you've got a bar that's, I forget what it was, less than a meter long, okay, 80 centimeters long, it really doesn't make sense that the stretch would be 10 to the 10th meters, because that's greater than the radius of the Earth, right? And so think about numbers in terms of their relative size. And if a number comes out to be just ridiculously large or ridiculously small, that's the time to go back and check and see what did you do. And often it's just a power of 10. It's a dropping a negative sign in 10 to the minus 10 or 10 to the plus 10. You put the wrong sign in, but go look for those, catch your mistakes. If you could catch them, that's often the distance. The difference, as I said, between a B and an A student right there is catching those kinds of mistakes. Any questions for me on how this problem went? And the strategies of working physics problems, as well as the strategies of getting physics problems right, which is always kind of the goal in the background. Questions? All right, well, then I'm going to move on to the next problem. I'll be breaking you up into groups here. We got 15 minutes left. And the only difference between this problem and the problem I did in the pre-lecture video last night is you also have to consider the moment of inertia of the skater's torso, okay? And it's given as 0.1 kilogram meter squared, as well as the moment of inertia of the skater's hand. And remember what we discovered on lab last week, that the moment of inertia is just the sum of these things. So like it's the moment of inertia of the torso, okay, right there, plus the moment of inertia of the hands, which you have to use a calculation for, right? M times R squared for the hands. And there's two hands, so you can either add it again or you can just double it, whichever seems to make more sense to you. Okay, and so the first thing I have you do is look at what's the initial moment of inertia with the hands outward, which I think is 0.8 meters. And then the skater moves the hands inward to 0.4 meters, 80 centimeters into 40 centimeters. And what's the change in moment of inertia? And then what must be the change in the angular velocity in order to conserve angular momentum? Questions on that? All right, then if I can find where, there it is, breakout rooms. We got what, 28 people. We'll create 7 rooms here, and hopefully I'll make it around to everybody to answer any questions. Make sure you get the problem right, and hopefully finish it before the end of the hour. See you in a bit. Oh, waiting on me.
Oh,
I didn't hit the button. My bad. Sorry about that. I'll be in the rooms in just a minute. Give you a second to get started on the problem, I guess.
I have a question.
Sure, what you got? I do this.
So,
Most people are more comfortable asking questions in groups of 3 or 4 than they are in front of all 30 people in the class. So yeah, absolutely. Ask away.
so for the initial moment of inertia, what we do is like the 0.10
Yep.
plus 0.5 times like 0.80 for the first one, and then like
And square that. Don't forget to square it.
yeah.
And then double.
Okay,
Yeah.
got it. Okay, and
And
we
then
have
it'll change from, and the only change will be it'll go from 0.8 meters squared to 0.4. And so the moment of inertia should go down quite a bit. And then here's the equation you'll be using. Did I put it on? I put it on the sheet. It's actually on the worksheet at the top. But let me share this with you. You'll be using this equation right here then. So you know you'll have found this. and this. And I guess we told you the initial speed, and you can leave it in revolutions per minute. Converting that to radians
Okay.
per second takes some work, so you can just leave that in revolutions per minute. Okay.
Okay.
Yep.
Thank you.
You bet. Share, and I need to jump to the other rooms. All right, you guys didn't make it to your breakout rooms. Where are you supposed to be? And where are you supposed to be?
Let's see. Is that
Dr. Jakolski. Dr. Jakolski.
Yep. What's up?
For the initial, is it 0.74?
0.74. Yes, exactly right.
And then for final, is it 0.26?
Perfect. Yep.
All right.
And then I'll just share it. Then you plug those two numbers with your initial speed of 100 revolutions per minute into this equation right here. Because I think you know the initial angular momentum, the initial angular velocity. I'm sorry, the initial moment of inertia and the initial angular velocity. So you know the initial angular momentum. The only thing you don't know is that term right there. You know everything else. So just solve for it. All right. I got a question from Sydney, so I'm running to her room. All right, Sydney, I got a question from you.
Yeah, we're just having a little bit of trouble just even trying to find where to start for this
Okay,
problem.
so I put up before I split you up what the equation is for the initial moment of inertia, right? How would you calculate that? Share my, actually, let's share this. We can do it right here. What is that? Well, I think we said what I wrote up was it's the moment of inertia of the torso, which is given that it is 0.10 kilogram meter squared, right? Plus the moment of inertia of the hand, and we're treating the hand as just a point object out at some radius. So mass times radius squared. There's two of them. I could either do this, just add the other hand in, or I could double those two terms, right? And so let me do the first one for the initial, and then the final you do exactly the same way. So in this problem, you're given that as 0.1 kilogram meter squared, right? And then let's see, I'm just going to double that. 2 times what's the mass? The mass is 0.5 kilograms. So you put that right there. And then the radius of, question?
I think the mass is, oh yeah, never mind, it is.
Yeah, 0.5. And then the radius, the distance the hand is out is 0.8 meters. And that has to be squared. And that's why you've got kilogram meter squared in the units. So that thing gets squared. Okay. And you put those all in your calculator. That's going to be your initial moment of inertia. Anybody got a number that they banged out on their calculator here? Okay, well, do that. What changes then? The only thing that changes in the final moment of inertia is that number goes to 0.4 meters, right? Brings it from 80 centimeters into about here at about 40 centimeters from the axis that they're spinning around. So that changes the moment of inertia. The final one should be less than because of that.
Okay,
And then all you do is put those numbers into conservation of angular momentum, because it seems to me that you know then all three of the things that are circled, and the thing you don't know is that initial angular velocity, or the final angular velocity, I'm sorry. You just don't know that. So put everything in, just solve for the thing you don't know. You don't have to change the units. Normally omega is in radians per second. I'm fine if you just leave it as revolutions per minute, RPM. Okay.
I did the calculation and I got 0.74.
0.74 is initial. That's good. And then just change the number from 0.8 to 0.4. And what do you get then?
Um, 0.13.
Did you double the two hands? It should be a little bit bigger than that. Like,
Okay.
or did you forget to add on the moment of inertia of the torso?
Is it 0.26?
0.26 it is, kilogram meter squared. Yeah. And so now you know what that number is, and you know what that number is, and you're told the initial was 100 revolutions per minute, right? So just solve for the final. Solve for that. All right. I'm gonna hit another room up. That should be good to
Thank
go.
you.
Okay.
Yeah.
And then I'm just going to keep it as 100 RPM.
Yes,
If he
you
says
can
it's
do that.
okay.
Yeah,
Okay.
you normally angular velocity, excuse me, should be in radians per second. That's just another unit issue, and just leave it as is.
Okay.
Do you get a number, by the way? I can check your numbers. Make sure.
Not yet. I'm
What'd you get
still
for your
writing
moments of inertia?
down.
The initial and final.
The initial moment of inertia, I got 6.5. And then the final, I got 1.7.
And I'm gonna let's check that number because I'm not sure
Okay.
I agree. It's all,
I got 0.74 and then 0.26.
that's what I got too. So I agree with those. Let me share real quick. There, I'm hitting the wrong button. Whiteboard. Share.
Oh, I used 5 kilograms instead of 0.5 kilograms.
That'll do it right there. That'll do it. All right.
Yeah.
Okay. So you guys got it.
I'm just
All right. I'm gonna run to another room here real quick, and then we'll meet back in the main room. All right. Any questions from y'all? Want to check any numbers to see if you got the right values?
I got 285 RPMs.
285 is the winner. Yeah, perfect. All right, then we'll end this, and we'll see you guys back in the main room.
sorry.
Three, still waiting for a couple more people to come on back. All right, I got 24. Looks like a couple groups are still working. All right, well, I think most people are back right now. Yep, now everybody's back. Just want to, I got one group declared their answer, 285 revolutions per minute, and you can leave it that way. If you want to convert it to radians per second, go ahead and do that, but the question allows you to leave it in revolutions per minute. And 285 was a number. I saw that person uploaded their solutions, so they're done. I got a little pop-up on my screen. So that's it for today. But remember, just having 285, that's not physics. Explaining what the change in moment of inertia was based on, well, there is no change in moment of inertia. Explaining what the change in moment of, there is a change in moment of inertia. You calculated too, explaining that and justifying the new speed with the change in the moment of inertia is the physics of the problem. So that's what you have to put on your worksheet. All right, any questions? see some of you in lab tomorrow. I'll pop in with some of you with Dr. Kim this afternoon. Have a great afternoon, great tomorrow, and we'll see everybody back on Friday. Take care.